So today we're going to talk about subgroups, cosets, and quotient groups. So in the text, this is Article 35 on page 24. So we have a group G, and for example, the integers or the symmetric group Sn matrix groups and so forth. And a subset H of G is a subgroup of G if, first of all, the identity is in H. Second, if A and B are in H, then the product A times B is in H. And third, if A is in H, then A inverse is in H. So this is the notation we use if we're writing the group operation as multiplication. If the group is additive, we would say the identity, which we often write as 0 in an additive group, is in H. And if A, B are in H, then A plus B is in H, if the group operation is addition. And if A is in H, then minus A is in H. So this is exactly these three properties translated from multiplicative language to additive language. Okay. Any questions about that? So subgroups have a lot of nice properties. So there's, for example, the following result I could call a lemma. A non-empty subset H of G is a subgroup if and only if, whenever A and B are in H, then A B inverse is in H. So instead of checking these three properties, it's enough to check one property. And the proof goes as follows. First of all, H, not empty, this means not the empty set, means that there exists an element A in H. And if you let B equal A, then AB inverse, that's A times A inverse, that's the identity. And that's an H. So this property immediately implies that H contains the identity. And if B is in H, then B inverse, which we can write as E times B inverse, is also in H, because that's of this form. So H contains the inverse of its elements. And if A and B are in H, then we know B inverse is in H. And so A times B inverse inverse is in H. But the inverse of B inverse is B, so this is just AB. So H is also closed under multiplication. So this is kind of a shortcut. If you have a non-empty subset of a group, if you could just show that AB inverse is in the subset whenever A and B are in the subset, then you know instantly that you have a subgroup. Any questions about this? No? another lemma. This is, for example, 35 beta in the book. Suppose we have a finite set of subgroups of the same group G, then the intersection is a subgroup. And the proof is as follows. First of all, every HI is a subgroup. So it contains the identity. So if E is contained in every one of the HIs, then E is contained in the intersection of the HIs. So the intersection of this collection of subgroups is non-empty and contains the identity. Second, if A and B are in the intersection of all these n subgroups, then A and B are in HI for all I. But HI is a subgroup. So AV inverse is in HI for all I. And so AB inverse is in the intersection of the HIs. So I'm just using the lemma I proved a moment ago that a non-empty set is a subgroup if AB inverse is in the set for all A and B in the set. Any questions? So these are proofs. Every proof, it's a finite set of statements, each of which has to be justified. Okay. Let's give one more example. I'll give two more examples, perhaps, of subgroups. Let G be a group, what is called the center of G. It's the set Z of G of all elements X in G that commute with every element of G, such that AX equals XA for all A in G. And the notation in the book, it's your choice what notation you use, is Z sub G. So either Z subscript G or Z of G like this, that's the center of G. And again, I can state this as a lemma. This is 35 delta in the text. Z of G is a subgroup of G. And the proof is very simple. First of all, if you take the identity EA equals AE for all elements of the group. So the identity is in the center. Second, if X and Y are in the center, then if I take XY times A for every element A in the group, by associativity, this is X times YA. But YA is the same as AY, so that's X times AY. And again, by associativity, this is XA times Y. And again, by associativity, this is X times, oops, make sure I'm doing this right. Yeah, this is XA is the same, because X is in the center. XA is the same as AX times Y. And by associativity, this is A times XY. So XY times A is A times XY whenever X and Y are in the center. So the product XY is in the center. So this set of elements that commute with everything in the group is closed under multiplication. And why does it contain the inverse of each of its elements? So that X be in the center and A be any element of the group, then we have AX equals XA, because X is in the center. So if I take this relation, if I multiply on the left by X inverse, and I multiply on the right by X inverse, what do I get? XA, XX inverse is the identity. This is X inverse A. And this is the identity, so this is A, X inverse. So X inverse also commutes with A. So X inverse is in the center. So you need to look at this proof for a minute or two just to figure out what's going on. And how can you tell if a group is abelian? So G is abelian. What does that mean? It means that AX equals XA for all X and A in the group, which means X is in the center for all X in the group, which means G is equal to the center. So a group is abelian if and only if all elements commute. So every element is in the center. So the center is the whole group. What is the center? Let's try to compute. The center of S3. So the S3, this is the permutation group on the set 1, 2, 3. Now, suppose I let X be equal to, let's say, the transposition 1, 2. And suppose I let A be equal to the transposition 2, 3. Let's compute X times A. That's 1, 2, 2, 3. It's the product of these two transpositions. Let's see, this sends 1 to 2, 2 to 3, and 3 to 2 to 1. So XA is 1, 2, 3. What is AX? AX is 2, 3, 1, 2. This sends 1 to 3, 3 to 2, 2 back to 1. And these are different permutations. So XA different from AX means that 1, 2 is not in the center of the group S3. And in fact, no transposition is. Suppose I take x equal to 1, 2, 3, and a equal to 2, 3. What is xa? So that's this permutation composed of this permutation. This sends 1 to 1 to 2. This sends 2 to 3, and 3 goes back to 1, so 2 goes to 1. 3 goes to 2. So xa is the permutation 1, 2. What is ax? Two, 3, composed with 1, 2, 3. This sends 1 to 2 and 2 to 3, so 1 goes to 3, 3 back to 1, 2 to 3 to 2. So xa is 1, 2, which is different from the transposition 1, 3, which is ax. So x is also not in, so this cycle 1, 2, 3 is not in the center of S3. And in fact, you can show that no transposition, no 3 cycle is. So the center of S3 only contains the identity. So S3 is as far away from being abelian as you can get. Nothing in the group commutes with everything else in the group. These are fundamental results about subgroups. And whenever you have a subgroup, you can define a very nice equivalence relation on the group as follows. So I have to say that everything I am saying now is very important. So that H be a subgroup of the group G. We define a relation on G as follows. For elements x and y in the group, we say that x is related to y if x inverse y is in the subgroup H. And I claim this is an equivalence relation. Why is that? Well, first of all, for all x in the group, x inverse x is the identity is in H. Because every subgroup contains the identity. So every x is related to itself. That means this relation is what is called reflexive. For all x and y in the group, if x is related to y, then x inverse y is in H. That's the definition of this relation. X is related to y if x inverse y is in H. But that implies that x inverse y inverse is in H. Subgroup contains the inverse of each of its elements. And the inverse of x inverse y is y inverse x. In general, the inverse of AB is B inverse A inverse. It interchanges the order. So the inverse of x inverse y is y inverse x inverse inverse. But the inverse of x inverse is x. So y inverse x is in H. So y is related to x. So if x is related to y, y is related to x. So that means this relation is symmetric. And the third thing we have to do is show that it's transitive. So if x is related to y and y is related to z, then x related to y means x inverse y is in H. And y related to z means y inverse z is in H. So these are two elements of H. And H is closed under multiplication. So x inverse y, y inverse z is in H. So this is x inverse, y inverse, that's the identity z. That's x inverse z, which means x is related to z. So if x is related to y and y is related to z, x is related to z. That means this relation is transitive. So what is the equivalence class of an element x in G? So this means the set of all y in G such that x is related to y. Related to y. And what is that? We again recall. We have H, subgroup of a group G. X is related to y if x inverse y is in H. So if you look at the set of all y, such that x inverse, such that x is related to y, that's the set of all y, such that x inverse y is in H. This means the set of all y, such that x inverse y equals H for some H in the subgroup. That means the set of all y, such that y equals, I just multiply by x, y is equal to xh for some H in H. And that's just the set we can call xh. Xh is the set of all elements xh, H and H. So for this relation, the equivalence class of X is the set XH. It's all elements that you can write as X times an element of H. And there's a name for this kind of set. XH is called a left coset of H. That is, I'm taking all the elements of H and multiplying them all on the left by X. So a left coset of a subgroup is a set that you get by fixing some element X in the group and multiplying everything in the subgroup H by that X. And because these are equivalence classes, for all elements X and Y in the group, we have either XH and YH, these two cosets, are empty, their intersection has nothing in it, or they're equal. So if you have a group G, you can partition the group into subsets, which are these left cosets. So here we have G, and you might have x1h, x2h, x3h, x sub kh. These are all the left cosets of G, and they partition G into pieces. What is the left coset EH? This is everything of the form E times H for H and H. But multiplying anything by the identity just gives you the anything. This is set of all H and H. That's just H. So the left coset of H obtained from the element E, that's the identity, EH is just equal to H. So one of these cosets is always the subgroup H. And then you have all the others. Now, if G is abelian and written additively, so if G is an additive abelian group, then the relation is X is equivalent to Y if minus X plus Y or Y minus X is in H. So you have this additive notation. And let's look at a very simple example of cosets. Suppose we let G be the integers and H to be 2Z. This is the even integers. So if X is some even number, then the coset X plus 2Z, this is all numbers of the form X plus Y, where Y is in the subgroup 2Z. But if Y is in the subgroup, I can write it as 2Y. So if we're all 2Y in here, because this is the even number, so every number here is 2Y. X, this is 2W plus 2Y. This is 2 times Y plus times W plus Y. This is just all even integers. So if X is even, 2W plus 2Z, this is my H, is just 2Z. If X is odd, then X plus 2Z, this is 2W plus 1 plus 2Z. This is all numbers of the form 2W plus 1 plus 2 times Y for any integer Y. Because again, my subgroup H is the even numbers. This is, I can write this as 2 times W plus Y plus 1 for all Y and Z. Again, this is just all odd numbers, which is the same as 1 plus 2Z. So for the group G equal to the integers and the subgroup being the even integers, there are only two different cosets. So we have the coset H equal 2Z and the coset 1 plus H or 1 plus 2Z, which is the odd numbers. So if here we have the integers, what are the two cosets? 0 plus 2Z, which just means 2Z, and 1 plus 2Z, the even numbers and the odd numbers. Just 1 second. Yes. What we're doing is not easy. It takes a lot of study time in a quiet place if possible, and a lot of pencil and paper to understand these concepts. Okay, any questions? Let's see, let me try another example. I've done another 2 examples. So one is an example we already know. So generalizes the example of the even and odd numbers. Let G be the integers under addition and H to be MZ. That's the set of multiples of M. So suppose we let X be an integer. What is the left coset X plus MZ? This is all numbers of the form X plus M. These are the multiples of M, M times MQ for any integer Q. What is this? This is the congruence class of X modulo M. So the set of left cosets of MZ is Z mod MZ, or Z sub M. This is the set of all left cosets, X plus MZ. X is 0, 1, 2, up to M minus 1. So this, and we already saw that we can add and subtract congruence classes. So in this example, the set of left cosets actually gives us a new group, which is an example of what's called a quotient group. Let's take another example. Suppose I let G be S3. So this is the set of permutations of 1, 2, and 3. We have the identity. We have the cycle 1, 2, 3. The inverse of that cycle, which is 1, 3, 2. And we have 3 transpositions. Tau 1 interchanges 2 and 3. Tau 2 interchanges 1 and 3. And tau 3 interchanges 1 and 2. So I have 1, 2, 3, 4, 5, 6. The symmetric group S3 has 6 elements. And I can take the subgroup H to consist of the identity, sigma, and sigma inverse. So these 3 elements form a subgroup. Let's calculate the left cosets. So the left coset 1, 2 is 1, 2H. This is, or let's say, so this is tau 3H. Tau 3 is the transposition 1, 2. 1, 2 times H. So this is 1, 2 times the identity, 1, 2 times sigma, and 1, 2 times sigma inverse. So we have to do this calculation. Now, 1, 2 times the identity is just 1, 2. what is 1, 2 times sigma? That's 1, 2 times 1, 2, 3. What is this permutation? This sends 1 to 2 and 2 back to 1. So 1 goes to 1. So I don't even need to write that down. This sends 2 to 3. This sends 3 to 1 and 1 to 2. So 1, 2 sigma is 2, 3. And what is 1, 2 sigma inverse? That's 1, 2 times 1, 3, 2. This sends 1 to 3, 3 to 2 and 2 back to 1, 2 to 1 to 2. So this is 1, 3. So this left coset consists of the other 3 elements of the symmetric group. So in this case, if I look at the left cosets of this subgroup, I get the subgroup and I get the 3 transpositions. It's really a very pretty decomposition. So it's very hard to understand this the first time you see it. The only way to understand it Yep. So let's look at another example. Suppose I take G again to be the symmetric group S3, and this time I let H be the subgroup consisting of just the 2 elements, the identity and 1, 2. So let's compute the left cosets 2, 3 times H and 1, 2, 3 times H. So 2, 3 times H, you multiply each element of H on the left by 2, 3. So you get 2, 3 times the identity and 2, 3 times 1, 2. And 1, 2, 3 times H, you multiply each element of H on the left by 1, 2, 3. 1, 2, 3 times the identity and 1, 2, 3 times 1, 2. So take a minute and do this calculation. 2, 3 times the identity, that's just 2, 3, because you're only multiplying it by the identity. So compute 2, 3 times 1, 2, and also compute these. And actually, it's literally take a minute or two, and I'll give you a chance to do it, and then we can compare our answers. So has anyone calculated the permutation 2, 3 times 1, 2? So this is composition of functions. This sends 1 to 2 and then 2 to 3, so 1 goes to 3. This sends 3 to 2, 2 goes to 1, so 2 goes, so this is 2, 3, and 1, 3, 2. That's the same as this is tau 1, and that's sigma inverse. What about these? 1, 2, 3 times the identity, that's just 1, 2, 3. And 1, 2, 3 times 1, 2. This sends 1 to 2 and then 2 to 3. This sends 2 to 1 and 1 to 2, so 2 goes to 2. This sends 3 back to 1. So this is sigma, and 1, 3 is tau 2. So these cosets are very important. You have a group and you're subdividing it into pieces. When you have a subgroup, these are the coset decomposition. This is the coset decomposition of G. So you might say, if we can define left cosets, the left coset XH is everything of the form X times H, H and H. And this is the equivalence class of the relation X is related to Y if X inverse Y is in H. You might say, well, maybe instead of multiplying everything in the subgroup H on the left by X, we multiply everything in the subgroup H on the right by X. This would be H times little x for H and H. And this is called a right coset. And in fact, these are the equivalence classes for a different equivalence relation, where we say X is related to Y if Y X inverse is in H. So here we have X inverse Y, here we have Y X inverse. And you can see Y X inverse is in H if and only if Y X inverse equals H for some H in the subgroup H, which is the same as saying if I multiply on the right by X, Y equals XH for some H in H. So the elements that are related to Y, X is related to Y, if and only if Y equals HX, if and only if Y is in the right coset. So we have a different equivalence relation when we look at right cosets instead of left cosets. So let me do this same calculation, but now with right cosets instead of left cosets.
Professor, can you move the page a little bit up, please?
Yep.
Thank you.
Right. So YX inverse is in H, means YX inverse is equal to little h for some element H in the subgroup capital H. If I multiply on the right, that says Y equals H times X, or Y, in other words, is in the right coset, that's it, HX.
Okay, thank you.
So let's do the similar calculation where I take G to be the symmetric group S3, H to be the subgroup consisting of just the two elements, E and 1, 2, which is E, and the notation that I've used, 1, 2, is the transposition, tau 3. And I calculated a moment ago that the left coset 2, 3H consists of tau 1 and sigma inverse. The left coset 1, 2, 3H consists of, no, this is tau 1, consists of sigma and tau 2. Sigma is 1, 2, 3. Sigma inverse is 1, 3, 2. Let's compute, instead of the left coset, let's compute the right coset, H times 2, 3. So that's E and the transposition 1, 2 multiplied on the right by 2, 3. So this consists of the identity times 2, 3, which is 2, 3, and 1, 2 times 2, 3. Again, this is a non-abelian group. The order matters. You cannot write 2, 3, 1, 2 instead of 1, 2, 2, 3. They're different things. What is this permutation? The first is just 2, 3. This sends 1 to 2, 2 to 3, 3 to 2 to 1. So that's tau 1 and sigma. And what is H 1, 2, 3? That's the subgroup H multiplied on the right by the 3 cycle 1, 2, 3. That's 1, 2, 3. E times the identity times 1, 2, 3 is 1, 2, 3. And 1, 2 times 1, 2, 3. Again, the order matters. You can't just change this. So 1, 2, 3 is sigma. This sends 1 to 2 and 2 back to 1, 2 to 3, 3 to 2. So this is sigma and tau 1. So 2, 3 times H is tau 1 and sigma inverse. H times 2, 3 is equal to tau 1 and sigma. They're different. 1, 2, 3 H is sigma tau 2. H times 1, 2, 3, the right coset, is sigma and tau 1. Again, they're different. So the left coset and the right coset, they're not the same thing. So let's just recall the definition. The order of a finite group G, finite group just means a group with only finitely many elements, is the number of elements in G. And it's denoted O of G sometimes for order, or G with absolute value signs around it. So for example, if you take the integers mod 2, That's two cosets, the evens and the odd. That group has order 2. S3, the symmetric group on 3 letters, we saw is equal to 6. And in general, the symmetric group on n letters has n factorial numbers. N factorial means the product of all the positive integers from 1 up to n. So S3 is 1 times 2 times 3, which is equal to 6. Now G be a group, and A, an element of G, that X be the set of all the powers of A, positive, negative, and 0. So you have A squared, A cubed, A to the 4th, A to the 0, which is the identity, but A to the -1, A to the -2, A to the -3, and so forth. You have all the positive and negative powers of A. When we have the exponent rule, A to the K times A to the L is A to the K plus L for all integers K and L. So H is a subgroup. And we call it the subgroup generated by A. In fact, it's a certain kind of subgroup. We call it a cyclic subgroup. So a cyclic subgroup of a group is all elements which consist of all the powers of a single element of the group. And it could be finite or infinite. If G is abelian and additive, and we sometimes write it as A in brackets. So the cyclic subgroup generated by A will consist of all multiples of A, 0A, 2A, 3A, 4A, minus A, minus 2A, and so forth. Set of all K times A, but you can't take powers, K times A, K in the integers. So in the case of an additive group, this is what a cyclic subgroup looks like. So for in Z, MZ, which is the multiples of M, is the cyclic subgroup generated by M. we could try to find, let's try to compute all subgroups of the integers. So let H be a subgroup of Z. So one example is H just consists of the number 0, because that's a subgroup. It contains the identity, which is 0. It's closed under addition. 0 plus 0 is 0. And it's closed under subtraction. So the set just consisting of the number 0 is a subgroup of the integers, sometimes called the trivial subgroup, because it is pretty trivial. Okay? Suppose H is not just 0. Then H contains some number m different from 0. If m is negative, then H also contains, it's a subgroup, so it contains the negative minus m, which is positive. So if H is not 0, then H contains positive integers. So let m be the smallest positive integer. Remember, positive means strictly bigger than 0. Positive integer in Z. So, sorry, not in Z, in the subgroup H. Then H contains all the multiples of m, right? It contains m, 2m, 3m, all q times m for all integers q. Suppose I take any number n in H. By the division algorithm, if I divide n by m, I get n is q times m plus a remainder. The remainder is between 0 and minus 1. But n is in H and qm is in H. So n minus qm, which is r, is in H. But r is between 0 and m minus 1. And m is the smallest positive number in H. So r cannot be a positive number. So r is 0. So n is equal to qm. So every element of H is a multiple of m. So if I want to know what are all the subgroups of Z, it's just all of the multiples of m for every non-negative integer m. So I now completely describe all of the subgroups of Z. Any questions about this? Suppose I want to find all subgroups of S3, which is, again, the identity, sigma, sigma inverse, tau 1, tau 2, tau 3. These are the transpositions. These are the 3 cycles. So first of all, I have the cyclic subgroups. What is the subgroup generated by? Well, first of all, the subgroup generated by the identity is just the identity. The subgroup generated by sigma, I have E sigma, sigma squared, which is the same as sigma inverse, and sigma cubed is the identity. So these 3 elements form a subgroup. I also know with the transposition, if I square a transposition, I get the identity. Okay. 1, 2 followed by 1, 2. 1 goes to 2 goes to 1. 2 goes to 1 goes to 2. 3 goes to 3 goes to 3. This is the identity. So for each I, the subgroup generated by tau I is just the identity in tau I. This is the same as the subgroup generated by sigma inverse, because sigma inverse is sigma squared. If I square it, I get sigma. So S3 contains 5 cyclic subgroups. And I claim there are no others. So if I take another subgroup, if it's different from one of these, it has to contain sigma, and it has to contain either sigma or sigma inverse. It has to contain a transposition. And if H is a subgroup of S3 that contains, let's say, sigma and tau I for some transposition I, then in fact H is the whole group. So S3 contains exactly 5 subgroups. Sorry, exactly 6 subgroups. Nope, sorry, that's right the first time. 5 subgroups. I have the identity, and I have the group itself, which is always a subgroup of itself. That's right, 6. I have the subgroup generated by sigma, which is the same as the subgroup generated by sigma inverse, 1, 2, 3. I have the subgroup generated by tau 1, subgroup generated by tau 2, subgroup generated by tau 3. So S3 contains exactly 6 subgroups. Let's say something else about cosets of a group. That H be a subgroup of the group G, that X and Y be in H. So we consider the left cosets XH and YH. And I can define a function from XH to YH as follows. Everything in X in this left coset is the form X times little h. Define f of X times little h to be y times little h. So this function from the left coset xh to the left coset yh, this is 1 to 1 and onto. Because everything here is of the form yh, so it's the image of something. And xh, every yh can only come from xh. So this says that the number of elements in xh equals the number of elements in yh. So all left cosets have the same number of elements. Now, if I have G, it's a union. So G is the union of its left cosets. So suppose G is finite. H is a subgroup. Suppose G has n elements and H has m elements. So here's my group G, and it's divided into pairwise disjoint cosets. I have x1h, x2h, x3h. Let's say they're k cosets. So every coset is non-empty. G is a finite set, so if you partition it into pairwise disjoint pieces, there can only be finitely many k pieces. So let k be the number of left cosets. So what I'm describing is as follows. Suppose I let G mod H, G slash H, be the set of left cosets of H in G. So this is x1h, x2h, up to x sub kh. So the number of elements in G mod H is equal to k. This is called the index of H and G. So if I have a finite group G and a subgroup H, there are only finitely many different left cosets, and the number of them, k, is called the index of H and G. But I also have that G is partitioned into these cosets. So G is the union of these cosets. That's the union. I goes from 1 up to k, x sub I h. So the number of elements in G, these elements, these sets are pairwise disjoint. It's the number of elements in the left coset. I goes from 1 up to k. But I just said that all these left cosets have the same number of elements. And if I take the left coset EH, for example, the cardinality of that is the same as the cardinality of H, which is M. So this is K times M. I'm adding M to itself, K times. So if N is the order of the group and M is the order of the subgroup, I have this beautiful relation between the group G, the subgroup H, and the index. The index will denote G colon H in square brackets. So this says that, this is actually a theorem. if G is a finite group and H a subgroup, the order of G is the order of H times the index of the subgroup in H. And so this says this number is this number times this. So corollary is in a finite group, the order of a subgroup must divide the order of the group. So this theorem has a name, it's called Lagrange's theorem. So let's just look at an example. So let me just restate this again. The order of a group G is the order of the subgroup H times the index for a finite group. So example, suppose we take the group S3. The order of S3 is 6. What are the divisors of 6? What integers, positive integers, divide 6? 1, 2, 3, and 6. If we take the subgroup H, consisting of just the identity, the order of H is 1. That's okay, 1 divides 6. Suppose I take H to be the cyclic subgroup generated by a transposition. So I have the identity and the transposition. So for this cyclic subgroup, it has 2 elements. 2 is a divisor of 6. If I take sigma to be the 3 cycle 1, 2, 3, the subgroup generated by sigma is the identity sigma and sigma squared, or sigma inverse. So this has 3 elements. And if I take S3 itself, that has 6 elements. So in this example, it's a nice example, but it's not necessarily universal. The order of every subgroup is a divisor of 6. And in fact, for every divisor of 6, there is a subgroup of that order. So this is a nice example of Lagrange's theorem. Okay. Questions about this? So this is really one of the central results in this entire course. And it's important to spend a lot of time to understand it. All right, so that's all I'm going to do today. Next week is the midterm. So just as a reminder, I'm going to send out a review sheet. So the midterm review will be on Monday, which is the 21st. And the midterm exam will be on Wednesday, the 23rd, from 9 to 11 a.m. At 9 o'clock, I will email out and post the exam on Blackboard. You have 2 hours. I mean, it's really supposed to be an hour and 40 minutes, but 2 hours to write out the solutions, convert it to a PDF file, and then upload it to Blackboard to the assignment section, just the way you do with your homework. Any questions about any of this?
Professor, are you, sorry to clarify, but are you gonna send the review sheet before the weekend?
Yes.
Great, thank you.
Yeah, no. You'll have 3 or 4 days to work on it, by Monday, certainly.
Professor, are you gonna have office hours for this week?
Yes, I'll have office hours. I'll set one for tonight, actually, and then Thursday and Friday as well. I might also have office hours over the weekend, because in case anyone would like.
Okay, you're gonna post the hours, right, in the Blackboard.
Yes, exactly. I'll post them and email them.
Okay, thank you.
Okay.